think
So welcome everybody. Today I will give a short presentation about the systems biology markup language, short SBML, and describe what it is and what it can do for you. So what is SBML? So SBML is a software data format for describing computational models in biology. So I would see this somehow like as HTML or some text file where you describe what a model is and what a model can do. And it makes sense to have such a standardized description language because people can exchange it and reuse it and easily understand what is in such a model. And especially you can also build software and tools on top of that. SBML is independent of any particular tool. It's just an exchange format, and what the tools are doing with that and how they're interpreting it is it's a different question. It's free and open, so there's no licensing fees to use that, and also the development is basically open. And it's a de facto standard in this field, like in the systems biology field, also more and more in the systems medicine field, it's a de facto standard for exchanging models. It's mainly built for a class of models which are called ordinary differential equation models. And I would say it's if you have an biological model which is an ordinary differential equation model, it's very likely that you will exchange it in SBML or that you will find SBML for such a model. SBML is developed via the community. There is like basically yearly meetings which come together and they discuss the language and develop it. And it's open basically for changes, and over time it changes also and adds new features. We use SBML a lot for describing the metabolism and metabolic models, for instance, for the organs in our physiological-based pharmacokinetic models. But we also use it for describing these physiological-based pharmacokinetic models. There's a large collection of models available in SBML. I'd say the best and largest collection is the biomodels. And there you find around 1,000 created models from the literature where people from biomodels tested that they can reproduce the results from actual publications. So there's a large set of quality models which are available. Most of them are ordinary differential equation models, but there are also more and more constraint-based models and other formulations like Petri nets for logical models or other logical model formulations. So what is SBML? And it's built modular, and it has like a core language, SBML core, which is mainly a reaction and process-based description of things. So in the end, you have species or entities in your model, and then you have processes which change these entities. And that's a basic concept, and this allows like to describe a lot of different things in biology. So metabolic networks also are pretty straightforward to get to this process process entity description. You just have the species are often the metabolites, and the reaction or the processes are the metabolic reactions or the metabolic transporters. But also in signaling cascades and signal transduction, you often have like a very similar approach. You sometimes have like information flow, but still the information is often represented by actual molecules. So you can imagine that in a more signaling cascade, the processes would be phosphorylation, dephosphorylation, and change of signaling state, and your different entities or states would be the amount of signal in a certain state. Like for instance, how much do I have of a phosphorylated entity and so on. Around this core, third example, like in our physiological-based pharmacokinetic models, often we have transport reactions. And so our processes are transport between different compartments, and like, for instance, from the venous blood to the organs and from the organs to the arterial blood. And this is like this transport, of course, is also like a reaction somehow, which transports something from one place, one compartment to another compartment. There are extensions around this core language to describe additional features. Some are specific for certain modeling frameworks, modeling concepts. Like for instance, FBC, it's an extension which describes constraint-based models. These are often like large-scale metabolic models where you do some linear optimization to figure out like, okay, how much can cells grow and so on and so on. But for that, you have to define like additional mathematical concepts like constraints and so on, which you normally don't have in this ordinary differential equation system. Okay, long story short, it is more like it's a different modeling concept, modeling framework, and to describe the things which are specific for that, you need an extension which can do that. Similarly, there is something which is called Qual. It's not here on the figure, but it's an extension for the logical networks where you basically have signaling states and you have transitions between the states. In the end, it's very similar to the reaction entity or process entity concept, just that you have like transitions and states between you go. And it's a different extension. There's comp, which is hierarchical model composition, and allows to combine and connect models. We're using that a lot like for the connections between the tissue models and the whole body models. And then there are other things like layout, groups, and distrib, which allow to do additional information. But I would say most of the things which we see is like the core. There's sometimes you interact with a comp for the composition, but you can bring down this composite models back to a flat core model by a process which is called flattening. So often you see like some part of comp, but it's going back to this core model, which is basically species and reactions. Importantly, you can exchange and make models reproducible with SBML. So it means if you have this file and give it someone else, she can run the same simulations and get the same numerical results. I would say that's the biggest thing, and especially you can also have like some testing of implementations. Like for instance, if you want to execute it, you need simulators which understand the model concepts and can execute it. Like for instance, for ordinary differential equations, you have to translate the model into differential equations and then execute the differential equations correctly. And if you have like one format, different simulators can implement the same things, and you can compare, okay, do I have any bugs in my simulators or do I get the same results? You have a lot of testing and for checking models and the validity. This is, for instance, that you have units, unit checking, but also things like automatic checking of equations in your systems. Often we're doing things like mass charge balance, and we use a lot like this annotations to ontologies to just describe what actually a model is. And so overall, there's a lot of features you get by putting your models into SBML. Especially you can use like a wide range of tools, like for instance for visualization, parameter fitting, and simulations. Yeah, but of course it has like some additional overhead somehow because you have to put your model into this language and understand what are the concepts you can describe in the language. And often this is it's not. You have to understand what it is and how it works to understand. Okay, it's what it can do. Overall, this is basically an XML format, SBML, and it has like different lists which describe the objects which are in the model. And then so the most important objects are compartments, which are basically locations where you can put your species and entities. You have the species, which are like objects which you put into the compartments, and then you have this reactions, which are the processes, and they change the amounts of the species in the compartments. So that's, I would say, it's the main thing. And then you have a lot of additional things which are on top of that and provide like functionality to, for instance, define functions, define rules, and define events and things like that. There's more like a more fine-grained things to make your model more complex, but at the core, things are basically compartments, species, reactions, and often like this parameters. Assignment rules are an important thing, and there you can basically calculate new values or new observables, is often called, from existing things. So if you have like parameters or species in your object, in your model, which are body weight and height, you could easily calculate the body mass index via an assignment rule. but this is a concept of you have state variables, which are really in your ordinary differential equations, and then you can calculate additional things, which are basically rules which you can calculate from what you have. But you don't really have to solve the differential equations for that, but you can just calculate it from the things that you have. Yeah, that's I would say the overall structure. And so often it's like the key challenge is how do you find an abstraction from your actual thing of what you model to this abstract language of things which are in there. For these physiological-based pharmacokinetic models, often this is pretty straightforward. So the compartments are basically the different compartments where things could be, like arterial blood, venous blood, liver, kidney, and processes are or reactions are basically the transport processes here. Parameters are things like, for instance, the blood flows to kidney, or the organ volumes, volume of the kidney and volumes of the liver. And assignment rules are really things like, okay, we're calculating from existing values, new values, like body mass index is a good example. Yeah, we also calculate the, for instance, the blood flow to the organs from the relative blood flow to the organs and the total cardiac output. So there are a lot of basically constrictions which you have in the physiology, and you put them into rules or in others of other of these mathematical constructs here. Okay. And so if you build these models, you often like interact with some of these lists of and put things in here and connect parts of these objects. What we're using for developing this is SBML utils, and this is basically some Python utilities for working and creating SBML models. So there's a low-level library which is called libSBML with language bindings and many like Python, R, Julia, C++, and so on. But it's very, very low level to create SBML. And so SBML utils provides basically a more high-level abstraction, which is very close to this data model of SBML. So it's it allows easily like to basically create this list, fill this list, and make the connections between the different objects. It supports many of these different packages. For us, the most important one are the core and the comp package, and it allows basically model creation, manipulation, also some other features, but with most of them you won't interact too much. In addition, like here's for instance one example where we create a parameter and then we can provide a lot of information, like for instance, what is the ID, what is the value, the unit, how it should be named, and then give some metadata about, okay, what is it, what are ranges, which is more like human readable documentation and also constants. And then tools can, like from that, you can create the SBML, and the SBML can be used to render this, for instance, or better understand what it is. So in this case, like this is a inhibitory constant for bilirubin for this importer of IgG. So this is one tool. The second tool what we often use is this SBML for humans. This is an interactive report where we can look at SBML and get an overview of the things in the model. There's basically a web application where you can upload your model and then have a look at what's going on in that. It has a lot of search and filter functionality, and can, like this sometimes important, it can also be easily used via like a web endpoint. Like for instance, here we could easily link to a model which already exists in biomodels and then directly get the report and get an overview, okay, of what is in the model. Like for instance, here we see, okay, this is a model, it has one compartment, 12 species, a lot of parameters. And then we could try to better understand what is going on. Here we see a lot of reactions between things, but it provides a bit more high-level overview of what this actual model is. And we can especially also filter for certain things here, and then only get a subset, like for instance, here only the reactions which are somehow connected to IL and so on and so on. So that's the second thing we often use to interact with the model. And the third thing is like the SBML, which is a library for visualization of these models. It has different views, and often what we use is like this entity process view to see, okay, what is actually in our model. Yeah, it has some nice integrations directly with SBML utils and so on, so you can create your models and directly visualize it. Yeah. here's some example of that, but that's normally what we do. Perhaps I would quickly show them the typical workflow, how we would create such a model. So what we normally have, we have like some environment for Python. In this case here, PyCharm, where we would create the models. Like for instance, here I would show a, let's see, what is a good example? Basically, we could use any of the models. Or I will just show Talinolol. Then often we have like this Python scripts which create some models. And I will just show a simple submodel here. Like in this case, is for Talinolol, which is cleared by the kidneys. And then we see we have certain compartments in here. And this is basically how we create this programmatically. We fill these lists up with those objects, and we say, okay, we want our model here. Our model has like some meta information. It has some name. It has some ID. It also has some units. And then we say, add to this model a list of compartments. Like here, it's a plasma compartment, a kidney compartment, a urinary compartment. Say like add some species. In this case, it's a Talinolol, which can be either in the plasma compartment X or in the urine. And then we add some parameters to this list of parameters and some reactions to the system. In the end, we can then call like this create model, and then it will create this SBML file for us from this general model definition. Just a second, I have to start Cytoscape. And so, so in this case, if we execute that here, this will basically create our file and write it in some location. Oh, because Jason expecting. Give me a second. Trace back. Oh yeah, okay. This Cytoscape is still starting. Okay, but it created the model here, and then we can have a look at the actual model file. So if you open this in a browser, you often see the metadata of the XML. If you look at the source code, this is really like an XML format where all this information is in there. So this looks complicated, but in the end, it's basically creates this whole list of things. So for instance, here you can see this list of compartments and list of parameters and so on. So this is basically the things which were created, but normally you don't interact with this machine readable description, but you would use like this abstraction level here, which provides you also like code completion and more like some checking that things are correct. And you just use this to create the SBML file. But of course, we could use this SBML file to just easily load that. For instance, now we could open this file. This is under PKDB models. So we created this Talinolol model and only the kidney from that. So I could import this created model now into this SBML for humans, and then I would easily understand, okay, my V extern, if I click on it, it's a physical compartment. It is plasma and so on. And here I only have a simple reaction, which is basically this reaction equation. It's irreversible, and it's in the compartment for kidney. And I can get a bit of feeling what is going on. Especially I can also get the units of my objects. So for instance, in urine, things are in amounts, in millimoles, and in the plasma, we have a concentration in millimole per liter. So that's one thing. On the other hand, we have the Cytoscape. Oh, well, I probably broke it somehow. What did I do? Oh yeah, I probably copied something in here. Yeah. On the other hand, we have this visualized SBML, which is directly connecting to Cytoscape, and then creates now for this created model like different views. And the most important view is here, like the species reaction view. In this case, we basically had 3 compartments, and we put the Talinolol in the plasma and in the urine, and then we had this one transport reaction which connected these two. That's basically what is in here. There are also more complicated views which show us, okay, the compartments and the reactions and the parameters and how is this all connected and where are the units and where do I have like ports and interfaces and so on. So this is more like the high level view, like often like for debugging or if something is strange in the model. Whereas the low level view is here, like I'm more interested in what processes are changing what. Yeah, often what is interesting to figure out, okay, how are the differential equations created from that? So that's also an easy way to do that. I can just I'll just quickly copy the information for that. So you can basically easily get a visualization of the differential equations. And what this is basically doing is saying, okay, in this case, it's creating this something which is called SBML to ODEs, and it's just reading the SBML and then creating a markdown description of the actual differential equations which we have in the system. This is often helpful, like to just get a feeling, okay, what is actually going on. And then you can see here, okay, in this case, yeah, we have certain units in our model. We have these parameters, which we defined here. This is basically the volumes of the different compartments. It's this renal function parameter, like that's fraction absorbed. We have certain initial conditions that basically our concentrations are all 0. And then we have like the actual ODE system, which is on the one hand, we have like here some equations. And then we have the actual differential equation system, which changes the two species. Like basically, yeah, the plasma concentration is reduced if this is put into the urine, and the urine is basically increased if this is put in the urine. And we see here like this automatically handles like this different compartment volumes and so on, which is often a big challenge if you want to create the differential equations. Okay, yeah, that's I would say that's most of what I wanted to show. Like a lot of things are like high level. I would say you don't have to understand everything. I think the different people should take different things away. So I think that at the lowest level you should take away, okay, this is just a description language for my model. And there are easy ways to create this model language, and this allows the exchange, and I can use all the different tools with the same model format. On a more higher level, I would say you should get, okay, there's a processor and the species in there, and this corresponds somehow to ordinary differential equations. And that's basically, I would say, the next thing. And the highest level thing is like really to understand, okay, what do these different components mean in there, and how can they affect the ordinary differential equations? How can they, what effect do they have, and so on. But often like this lower level abstractions are totally fine for you. And the thing is more like, okay, you have to understand that you have certain data which you can then compare to certain of these variables in the model, and you don't care too much about how the model is doing. It's more like on a high level you want to know, okay, yes, there is something in the kidney which is putting this from the plasma in the urine. Okay, how this works, it doesn't matter, but there is like something in there, and I can compare these rates of urinary excretion and the amounts in the urine with what I have actually in the model. And so I would say there's different ways to look at it. Don't worry if you there's a lot of mathematical and computational science in there at different points, but you don't have to get everything. I think the taking away the basic messages is the important thing here. And of course, it makes also like life much easier, like to collaborate and work together and reuse models, because everybody's using basically the same language. It's like this a Tower of Babel problem when everybody is speaking a different language, also like in the computer model description, then nobody can exchange or like understand what the other people are doing. And here it's more like by having some common understanding, which is a good compromise, it's much easier to reuse and understand what other people are doing. Okay, I would say that's about that.